Welcome back to a lecture series on statistical mechanics and molecular simulations. Recently, we've been discussing the canonical probability distribution and how this relates to statistical properties of atoms moving around in a system and how that can lead to emergent behavior that we see in thermodynamics. Well, in this lecture, what I want to do is go over some of the applications of the canonical ensemble to some important results that you might have seen before in other courses. So the first thing we're going to explore is something called the Maxwell-Boltzmann distribution. And this distribution, Maxwell-Boltzmann distribution, this is a distribution which shows if you have some particle or some system of a lot of particles, and let's say you tagged one particle, and you were to ask, what is the distribution of the momentum of that particle? And of course, this is a probability distribution, right? So the idea is you have some system, you have a bunch of particles in the box, let's say, or in the system, flying around. In this case, we'll say there's no external field so that we can write the Hamiltonian as being equal to a summation over all of the momenta for all particles I equal 1 to n, plus some interaction term. So these particles are then interacting based on where they are in space. And we'll say, I think we use that notation. So we have particles flying around obeying this Hamiltonian and evolving according to Hamilton's equations of motion. And we want to know if I were to tag a single particle, so this will be our special particle, the one I circled in green. If I were to look at a probability distribution function on its momentum, or let's say the magnitude of its momentum, and the probability of the magnitude of its momentum, what would it look like? Well, it would have some form, right? We're gonna calculate exactly what this is, but how would we get there from the canonical probability distribution? Well, recall the canonical probability distribution is this rho of QF, PF, and evaluated at a specific point in the phase space was equal to 1 over C e to the minus beta h, evaluated over that point in the phase space. So how could we go from this probability distribution on many particles to a probability distribution on a single particle? Well, the answer is to do integration, right? We can actually integrate out all of the other terms and leave only one. So let's suppose that our tagged particle we're going to label as particle 1. So if we want to get to this probability distribution rho, we're going to integrate over all of the momenta that are not equal to 1 and all of the positions. So all of the pi not equal to 1 and the q, and we have to, of course, do that on both sides. So pi not equal to 1 and q. And of course, on this side, what that's going to leave us with is this rho of P1. And then we will have integrated out all of these integration variables aside from dP1. So to find this distribution, we just have to evaluate this, this right-hand side, right? So how can we do that? Well, first, let's just write it out. So, of course, C is a constant here. So we're going to pull it out of the integral. So we have the double integral now. P I not equal to 1 Q of e to the minus beta h dQf dPf. So we just need to evaluate this integral. Now, before I go to the next board, let's evaluate C, this partition function. So remember, C was a normalization condition on our probability distribution. So all we need to do is integrate over all of the momenta, all of the positions of e to the minus beta h over the entire space, right? Well, let's substitute in our Hamiltonian. We now have c is equal to this double integral of e to the minus beta times this summation from n I equal 1 of pi squared over 2mi. And I'm going to separate this in one step because what we're going to do is add this here, but that's the same as multiplying by another exponential function. So we're going to say times e to the minus beta phi of q n. So that's the entire interaction configurational part of the integral. And then of course dqf dpf. And these are over momentum and position. Now we can see here that one of these terms is dependent on the momentum and one of them is dependent on the position. So we can split up the integral. So we can say that c is actually just equal to the integral over all of the momenta of e to the minus beta times this sum pi squared over 2mi dpf, so its own integral, right? Times a second integral, which is this configurational integral, e to the minus beta phi dqf. Now we're not going to mess with this term. We don't need to do anything else with this guy, because what's going to happen is we're going to, in evaluating the integral in the numerator here, this is just going to come out and we're going to be able to cancel it. But this guy is important. So what is this integral? Well, this is a Gaussian integral, right, of a specific form. And we have a sum in the numerator here. So we have a lot of integrals. So let's think about how we can break this guy up. Well, our integrals over all momenta, so P1, P2, all the way out to the n particles of the system. And notice that each one of these terms only depends on a single one of these at a time. So when we have this dpf, right, we can actually split this integral up into n integrals across all the particles in the system, right? So this is really equal to the integral of e to the minus beta p1 squared over 2m1 dp1, right? Integrated from momenta can take from minus infinity to infinity, right? And then we can just repeat that all the way through the n particles, e to the minus beta pn squared over 2mn dpn. And then of course we have what I'll call the configurational integral. We'll just give a special name. Let's call it theta. So times theta, which is the configurational part, right? Well, each one of these integrals can be solved pretty readily, right? And we have a product now of these integrals. So this entire thing is going to be equal to a product. Let me get a better. This entire C here is equal to the product over all the particles in the system of, if you were to evaluate this out, you would have 2 pi mi over beta. And I believe that's to the 3/2 here. And the reason for that is that each one of these P's, right, P1 is technically 3 components. It's P1x, P1y, P1z. So you can further split this into 3 integrals in x, y, and z. Each one has a solution of 2 pi mi over beta to the 1/2. And when you multiply all 3 together, you get this cube on top. And so then you have to solve that for each integral, so all over n, and that gives you this product. And finally, that's multiplied by our configurational part, theta. So we've calculated C here, our partition function. So now what I'm going to do is I'm going to erase the board, rewrite this C into this expression, and then we're going to evaluate this integral, which you can see is actually just exactly the same, except now we're not going to integrate over one of the momenta. Okay, so let's rewrite rho. We have rho was equal to 1 over c times this double integral, and specifically we're looking for rho of momentum 1, dp1. And I suppose I should clarify these are vectors, right? Because we have components in the x, y, and z directions. So this double integral over the p's where I is not equal to 1, which is our tagged particle, q of e to the minus beta h dpf not equal to 1 and dqf divided by c, which we just calculated over here, is this product over all the particles in the system of 2 pi mi over beta to the 3/2 times theta, which is our configurational integral. So now we just need to evaluate this numerator, right? Well, just as last time, our Hamiltonian can be separated into a part that depends on the momentum and a part that depends on the configuration. Now, in the configuration part, we do the exact same integral. So we're going to get a factor of theta out, right? So I'm just going to rewrite this denominator here. This was our partition function, theta, right? And when we evaluate over this QF, we're going to get the same theta, right? But now we have something a little different, right? Now our integral isn't over P1. So one of these terms in the Hamiltonian is going to pop out here. E to the minus beta of P1 squared over 2M1 dP1, right? This is not being integrated out. What is being integrated out is everything else, pi not equal 1, of e to the minus beta times the sum. Now we're going from n, from I equal 2 to n, because we're skipping the tagged particle, of pi squared over 2mi dpi. And then of course I've just rewritten this so that I have more space, and our theta can go there. And then of course this I is not equal 1. Okay, well, we can cancel this configurational part immediately. That's why we said we didn't have to do anything more with it, right? And we can also notice that this integral is the same as the integral to get this, except now we're going from I equal 2 to n rather than I equal 1 to n. So fully simplifying this expression out, we get e to the minus beta p1 squared over 2m1 dp1 times a product from I equal 2 to n, right, of this same value here, 2 pi mi over beta to the 3/2, divided by the same product, but now we'll have the indexes go from 1 to n rather than 2 to n, right? And I'm just going to call that index j here, 2 pi mj over beta to the 3/2. Now what's going to happen? Well, all of these are contained in this product, except for one single term. So all of these are going to cancel with all of these, except for the term when j equals 1, which is 2 pi m1 to the 3 halves. So that's the only term that's left over. So consolidating all these terms, we get that this probability distribution, this Maxwell-Boltzmann distribution on the momentum, is equal to, and let's rewrite all this in a way that's convenient. First, this is a constant, it's to the 3 halves. So what I can do is I can flip this to make it to the minus 3 halves, and then rewrite it, and then flip it back to get it to the numerator. It looks cleaner, I think. So technically right now this is to the minus 3 halves, and if we flip the inside we make it to the plus 3 halves. Yeah, so this should be then beta times 2 pi mi all in the denominator, right? So 1 over, and you can verify this yourself. And I'm going to rewrite beta as kBt. So we get 1 over 2 pi m1 kBt to the 3 halves times this e to the minus beta, and we'll plug in for beta here. So we'll do e to the minus p1 squared over 2 m1 kBt times dp1. So this is your Maxwell-Boltzmann distribution. And you can see immediately that this is a Gaussian, right? This is a Gaussian function. So it looks like if we were to draw it, something like this, where the maximum or the expectation is at this mode of the Gaussian distribution. And then of course the spread of the data can be described by things like the variance or higher order moments of the system. So this is the famous Maxwell-Boltzmann relation result. And what is it? Just to reiterate, it is a probability distribution on the momentum of a tagged particle in a system with the Hamiltonian that we described earlier, which had kinetic parts related to the 1/2 mv squared of the momenta, or of all the particles. And it also had that configurational part, which was dictated by the interactions between the particles. And you can see the way we got there was just by integrating out all of the contributions to this canonical distribution function, aside from that one tagged particle's momenta, giving us a Gaussian distribution known as the Maxwell-Boltzmann distribution. The next theorem I want to talk to you guys about is an application of the canonical ensemble, is the equipartition theorem. Now, the equipartition theorem is the idea that each degree of freedom in the system has the same contribution to the total energy of the system. And the reason that you might think of this is that before, when we had quadratic terms in our Hamiltonian, each quadratic term in that e to the minus beta h contributed to the total energy, a value of 1/2 kBt. So the question is this just a product of the math we've done so far, or is this actually a more general result, right? And so to think about this, let's consider a system in which we isolate a single term in the Hamiltonian. So we have our Hamiltonian, which of course depends on, it's the sum of the kinetic and potential energies, it depends on the momentum and the coordinates or the configuration, right? So this h, we're going to say we have one term that's quadratic, and we're going to call that aq1 squared, and plus some other function of all the other variables. So the qf's not equal to 1, and the pf's. And the question is, okay, well, if I take the expectation of h, I know that I get the internal energy of the system, right? But what if I take the expectation of just this single quadratic term? Well, the expectation of this single term is equal to the internal energy contribution from this one degree of freedom, right? And of course, if all of these were quadratic, we would then have the 2f two F terms, right, that pop out. And maybe for notation's sake, we shouldn't use, no, I think we're fine. So the question is, what is the expectation from this single contribution, this single quadratic contribution? Well, we can calculate that by taking its expectation. Now, what is the definition of the expectation? The expectation is equal to 1 over c integral over all of the p's, integral over all of the q's, of e to the minus beta h. Here, h is a q1 squared, and then we'll split it up, e to the minus beta little h, right? Because there's a sum in here, it would be a sum in the exponent of this of the exponential function, which can become a product of two exponential functions, over all the q's and all the p's. Now, I'm missing something here. We have this integral, of course, but what I forgot to include is that for the expectation, we need to take this value and put it inside here, a q1 squared. So this is what we need to evaluate. Now, to make it simpler, let's evaluate c first, this c. Well, just like last time, this is just equal to the integral over the entire, or over all p's and all q's of e to the minus beta h dqf dpf. Now, of course, we've isolated only q1 here, right? So in doing so, what we can grab from this is that, let's see, the integral over all the p's and all the q's except for q equal 1 is the exact same as the numerator. So the only thing that will be different is that one integral over q1 squared. So the way I'm going to write that is integral e to the minus beta of a, or minus beta a q1 squared dq1 times everything else, which we'll call theta. So theta is just, and we'll write it out, theta is just all the p's, all the q's for which q is not equal to 1, over e to the minus beta little h. And of course, the q is not equal to 1 here. And I'm just going to call this entire term theta. And in the numerator, we get the same theta to pop out, and our remaining term is just now this integral over a q1 squared e to the minus beta a q1 squared dq1, and of course the rest of it is just theta over c, which is the integral of e to the minus beta a q1 squared dq1 times theta. Well, those just cancel out, right? And now that we're here, I'll leave it as an exercise to show that this reduces to 1/2 beta to the minus 1, or equivalently 1/2 kBt. What this shows is that each quadratic contribution to the Hamiltonian contributes a 1/2 kBt to the total energy. Now, if you were to look at the total energy of the system in which every term was quadratic, well, if you have f degrees of freedom, or in this case, 2f degrees of freedom, f in the coordinates. So you have f coordinates and f momenta. Then each quadratic degree of freedom in here will contribute to 2f, and then you multiply that by the internal energy that each imparts on the system, and you get that the total internal energy for a system with 2f degrees of freedom is f kBT. So this is the equipartition theorem in a very, using a very simple application of the canonical distribution that we have so far. And this can have some far-reaching implications. For instance, if you look at the motion of molecules, you could look at each degree of freedom, each degree of freedom which is quadratic in the Hamiltonian, and say that the internal energy of that molecule should be equally distributed across all of those degrees of freedom, whether they're kinetic or rotational or translational, any of that, right? They're going to be equally distributed across. And what's so beautiful about it is that it falls out directly from just some simple arguments that take advantage of this canonical distribution. So next time, what we're going to get into is the fact that so far what we have done is actually not consistent with classical thermodynamics. And we'll see why in the next lecture. But as a preface, I want you to look back and consider what were some important properties of the free energy. Remember, free energies were extensive, meaning F of, and I guess here I'm saying the Helmholtz free energy F, which is a function of T, V, and N. T is, of course, intensive. But if we take Ft of lambda V, lambda N, this should equal lambda F of T, V, and N. However, what we'll find is that the F we've derived so far in StatMech does not satisfy this equation. So far, we have F equal minus kBT log C. So before next lecture, if you're feeling interested, try to show that this is not extensive. Now, to make it extensive, we're going to have to actually use some ideas from quantum mechanics. And furthermore, we're going to have to complete this partition function to solve another issue related to the uncertainty principle. So thank you guys for listening, and we'll see you next time.